today's lesson, we will be solving absolute value inequalities. If you'll remember, in chapter 1, we had a lesson on solving absolute value equations. We'll be building on what we learned. These are some important notes to write down. Remember, an inequality that contains an absolute value expression can be written as a compound inequality. The definition of absolute value. The absolute value of a number is its distance from 0. So the absolute value of a number that's less than 8 represents all real numbers whose distance from 0 is less than 8 units. Now, graphically, if you think about this on the number line, that can be represented by an interval, the interval from 8 to -8, and everything in between. When an absolute value inequality contains a less than symbol, it's an intersection, and it looks like this. It's an and statement. Here we have a table to organize some of our information. The inequality, the absolute value of a number less than 8 asks, what values of x have an absolute value less than a? The solutions are numbers between -a and a. Let's write that in numbers. You don't need to write the words for that. Let's write the numbers. So if we have the absolute value of a number less than 5, here's our compound inequality. We write that as -5 is less than x is less than 5. Let's also copy the graph for this. Graphically, we're talking about the absolute value of a number less than 5. We're looking at the numbers between -5 and 5 on the number line, and everything in between. These are open circles because the boundary points -5 and 5 are not included. Don't worry about the algebra on this. Take a look at the real examples. Now, the same properties are true for inequalities that have the symbol less than or equal to. So this is the case where we have a less than statement or a less than or equal to statement. Let's look at an example. Copy this example down. The absolute value of the number -3 is less than -1. All right. So our first step, just as it is for writing or solving absolute value equations, is to isolate the absolute value expression. In other words, the part that is in the absolute value bars. And that's the x. In this case, it's just the x. All right, there it is. So to do that, you're going to add 3 to each side, and that gives you the absolute value of a number less than 2. Let's think about this. This represents all real numbers less than 2. Less than 2 on the distance from 0. So that will represent numbers between -2 and 2. To graph this, we're going to put on our boundary points at -2 and at 2. And we're looking for all the numbers in between. Any number in between -2 and 2 is a solution. So it's right here, here to here. That's our solution. That's our graph. One more example of this type. Again, it's a less than or equal to sign. So we're looking at all numbers that are a distance of 2 or less from 0. Excuse my markers, they're not working very well. Looking at all the numbers between 2 and -2. So when you rewrite this as a compound inequality, since we're looking for numbers between 2 and -2, that's what we write. -2 is our left boundary, our minimum. 2 is our maximum, it's our right boundary. And we have the inside expression x minus 1. To solve this inequality, you do it just as we did for solving compound inequalities. Since 1 was subtracted from x, we're going to add 1 for every part of the inequality. That gives us our resulting compound inequality. -2 plus 1 is -1. -1 plus 1 is 0, so we're just left with x. And 2 plus 1 is 3, So here we have our compound inequality. Our boundary points are at -1. That's a closed circle. And at 3, that's also a closed circle. And then everything in between. Here's our graph. It's also an interval, an intersection. Now let's look at absolute value inequalities that have the OR statement. In this case, we're looking at the absolute value of a number that's greater than 8. If you think about this, this represents all real numbers, all real numbers whose distance from 0 is more than 8 units. Oh, we just went for a ride there. Let's try this again. All right, so I want you to copy down these notes. The absolute value of the absolute value of a number is greater than 8. So that would be numbers that would be further than 8 units away from 0. When an absolute value inequality contains a greater than symbol, this represents a union. It's an OR statement, and they go away from each other. Now let's look at the table. Study the table. Since you wrote the words above, you do not have to write these words, but I want you to think about it. Here we have a greater than symbol, so we're looking at numbers greater than 5. Any numbers greater than 5 or -5, because we're looking at the absolute value of that. I want you to copy the graph. So the graph looks like this. If we use the number 5 and -5, so the absolute value of a number is greater than 5, we're looking at numbers that are 5 units to the left of 0 and 5 units to the right of 0. So that's going to be at this point here at -5 and at 5. Copy the graph. You don't need to copy the algebra. Here's an example of an inequality, an absolute value inequality using the OR statement. All right, so we're looking at values greater than something. Our first step is to isolate the absolute value expression, just as we did for solving absolute value equations. We do this by subtracting 3 from each side. That gives us the absolute value of a number plus 2 is greater than 2. Now, we're looking at values greater than 2, so we're going to be graphing numbers that go away from each other. We're going to rewrite this as a compound inequality. Here's a tip for remembering. Remember, less than is and, greater is or. So associate the word than with the word and, associate with the greater with the word or. It will help you remember which way to put your inequality symbol. So we're looking at the two cases. Once we've isolated our absolute value inequality expression, we're looking at the two cases where we have the distance of x plus 2 is less than -2, and the absolute, x plus 2 is greater than 2. Now to solve for x, we're going to do the same thing everywhere. We're going to subtract 2 because 2 was added to x. Once we do that, we have our resulting simple inequalities. We have x is less than -4. We have x is greater than 0. To graph our solutions, we're going to put a boundary at -4 right here. And it's open circle because -4 is not included. I'm going to be shading in the values less than -4, so that's to the left. Over here, I have x greater than 0, so I have a boundary at 0. It's open because 0 is not included. And I have to shade in the numbers that are greater than 0. So I'll be shading to the right. Here's my OR statement expressed as a graph. Here's an application problem. Let's think about this. A pediatrician recommends that a baby's bath water be 95 degrees Fahrenheit, but it is acceptable for the temperature to vary from this amount by as much as 3 degrees. Thinking about that, Let me find that back again. Got a commercial break, I guess. Here we go. All right, here we go. Now, here's our example. Here's our pediatrician. So the baby's bath water can be plus or minus 3 degrees. It has to be 95 degrees, but it can be plus or minus 3 degrees of that. So to write that, you can think of that as its absolute value inequality. We want the temperature to be within 3 degrees. So we're going to write that as T plus 3, excuse me, T minus 3. I have a little mistake there. There should be a minus sign right there and right there. Sorry about that. So to rewrite this as an interval, we'll have -3. Let me just rewrite it right here. -3 is less than or equal to our temperature minus 95 degrees. T is our ideal temperature. So if it's 98 degrees, that's okay because that's within 3 degrees. If it's 92 degrees, that's okay because it's within 3 degrees. So here's our interval. When we solve that by adding 95 to each side, we get our interval of acceptable ranges. The acceptable temperatures of the bath water would range from 92 to 98 degrees. And we have one more. This is our last slide, but here's a big idea. You better write this one down. I'll be looking for this. Here's the big idea. Sometimes the solutions of an absolute value inequalities are all real numbers or no solution. I'll give you an example of each. Here's the first example. We have the absolute value of a number plus 4 minus 5 is greater than -8. So first we'll isolate that absolute value expression by adding 5 to each side. So that gets rid of this 5, and -8 plus 5 is -3. Let's think about this now. This looks difficult, but it's not. So I have some number, and we're saying that it's once we take the absolute value of this number, its distance will be greater than -3. This will always be true because this value will always be greater than -3. An absolute value will always be greater than -3. In fact, it's always greater than 0. It'll be 0 or greater. So if you have an absolute value expression that's greater than a negative number, that's always true. It's true for all real numbers. Let me write that down again. This is a big idea. True for all real numbers. This is a tricky one. You might go on to the homework website and check out example 4 for lesson 7 with Dr. Berger. Here's an example where there's no solution. In this example, we have the absolute value of a number minus 2. Excuse me, I should say that is a number minus 2. Its absolute value plus 9 is less than 7. This time, when we solve for the absolute value expression, we get some number, take its absolute value. And we're saying the absolute value of this expression, of this number, is going to be less than -2. That cannot be true because an absolute value will always be positive. It will always be 0 or above. It can never be negative. Never be less than -2 because it can never be negative. Since this is a false statement, there's no solution. Again, this is confusing to you. See example 4 on lesson 2-7 video tutorial. That's all for today. You'll be coming in tomorrow to practice these. I'll see you then. Thank you.